Welcome to the Projectile Lab. Today we're going to look at kinematic equations in 2 dimensions. So basically the lab consists of firing a cannonball and measuring the range of the ball, where it lands. So we have covered quite a bit of it in the lecture, and today we want to see if we can actually predict the range of the ball if we know its initial velocity, and then firing it and measuring it and compare it with our prediction, right? So let me just first start with a simple figure. And what we have here is the projectile. You launch a cannonball or you throw a football, whatever it is, and it's moving in 2 dimensions because x is your 1 dimension and y is your another dimension. And the ball will go up and will come down at a particular position on the x-axis, and we call this one the range. If we designate our initial position as xi and the final position as xf, then the range r will be calling it as simply xf minus xi. What we can do is actually resolve this velocity vector when you throw the ball or fire the cannonball, and the velocity vector can be resolved into 2 directions. So one is the Vy, the other one is in the Vx. So Vy and Vx. So this is my velocity going this way, and when I take the projection of it on x and y axis, I'll get Vx and Vy. So Vx is down here and Vy is down there. So obviously your total magnitude is basically the square of these guys, and you add them and take the square root of them, and that's the velocity. This is the velocity vector going that way. We also need to know one more thing. It's the angle at which you are throwing the projectile or throwing the ball, and we call this angle theta. So our job will be to find out what this r is. Now, as I mentioned in the class, if you actually throw a ball or anything, for example, this pen, its velocity, if you ignore the air friction in the x-axis, doesn't change. It does not change, okay? What changes is the y velocity. Why does the y velocity change? Because, of course, it is subjected to gravity, right? So when you throw a pen up, it slows down and comes back down is because the gravity is pulling on it. So it is constantly subjected to the acceleration due to gravity, which is minus 9.8 meters per second square. So let's say that I round it off to 10, minus 10. So if I throw this pen with a velocity of 10 meters per second, it will only take 1 second to get to 0 velocity. And then when it comes back to my hand, it will again gain that 10 meters per second. So it will take 1 second to go up and 1 second to come down. But basically, I can predict the time it will be in the air. So what happens again is that Vx does not change, Vy changes. So if I know how long that ball will be in air, I can simply take the x component of the velocity and multiply by the time t. And the t is the time it should be in the air, okay? So if I can figure out, if I throw a ball, that how much time it's in air. Actually, it's kind of funny to say when it is in the air, because we're not taking into account the air, because we're ignoring the air friction. So I can just simply multiply that with Vx, and I get the total range. So let's look at another kinematic equation, and the other kinematic equation is our second kinematic equation, yf minus yi equals Vyi, that's a V by the way, t minus half gt square. Usually this is plus half at square, right? But what we have taken is that a is negative g. It's negative because we are taking everything going up as to be positive, and we know that the acceleration is always downwards as the ball goes up, it's always slowing down downwards. But remember that the velocity in this direction doesn't change. So what I can do is that if I can actually determine the time and plug that in here, I'm all set. That's basically my experiment. So what's YF minus YI? Well, YF minus YI is basically where you are firing the ball and where you are finishing. In this case, you can see that YF minus YI will be 0 because the Y position, it goes up and comes down. The Y position is the same. For this particular lab, we're not going to fire it like this. What we have here, and I'll show you the equipment in a second, that we have a cannon, and we're going to fire it, and it will go up, and it will come down to a particular position, and that's my YF. My YI will be basically where the ball goes out of my barrel of the cannon. Okay, so that will be my YI. And you can see right away that if going up is positive, then YF will be a negative number because let's say that my YI is 1 meter and the ground will be 0 meters, so 0 minus 1 would be minus 1. So it will be a negative number. This will give me a negative number. So then what I can do is that if I know this, if I knew the Y component of the velocity, and you can see right away, this is a quadratic equation in t squared, right? So we have to solve that quadratic equation. We have done that in the class, but this is our opportunity to do it with our hands. So what will happen in the end that I will simply take this as half gt squared minus vyit plus yf minus yi equal to 0. That's my equation. It's also a kinematic equation because there is no force involved, but you can see that it's a quadratic equation. Basically, your quadratic equation is almost like it goes as at squared plus bt plus c equals 0, where t is your unknown or variable, right? And you can solve your quadratic equation, and we're going to do it right after our experiment to solve that how much time the ball is in the air. But first, what we have to do, we have to find out both Vx and the Vy initial. So let me reiterate one more time. Vy initial is the Y velocity when you fire the cannonball right here. But as the ball goes up, its Vy velocity actually goes down, but then it comes back down, its negative velocity increases, right? On the other hand, Vx never changes. Again, Vx never changes. There is no acceleration in Vx. Whatever I determine my Vx will be there also the same number, okay? One more thing I should write down is that if I can determine the velocity, then Vx component would be V cosine theta initial, and Vy initial would be V initial sine of theta. So basically those are the projection. V cosine theta is this guy, you take the projection on x-axis, and V sine theta is this guy, you take the projection on the y-axis, right? So remember this, I'm going to give you the angle so that you can simply plug in there and get that. Well, right now we are going to do an experiment, and we're going to find out what my initial velocity of the cannon will be, and you will get to see the entire equipment at the same time, okay? All right, so what we have here is our cannon, and right in front of the cannon is our photo gate. What will happen is that when I fire the cannonball by pulling on this string, the ball will first go through the first photo gate, and it will interrupt a laser beam there, and a timing will start. And then it will interrupt a laser beam on the second photo gate, and the timing will stop. So that will give us the time interval for the cannonball to cross from one photogate to the other. And if we know the distance between these two photogates, we can divide the distance by the time interval, and we get the initial velocity of the cannonball. So my first job would be actually to measure the distance between these photogates, and I measure it. It's 10 centimeter. It's a little bit off than 10 centimeter, but I will take that. So 10 centimeter is 0.1 meter. Okay. The other thing that I need to be careful about is the angle that I'm going to shoot my ball at. At this point of time, it's at 30 degrees. So we need that number because to calculate the x velocity and the y velocity, you have to do sine of 30 degree and cosine of 30 degrees. And the last thing here is my photogate display, and I have that on the pulse, so that what will happen is that the pulse determines that it will have a start and it will have an end. So let's do this. I'm going to use this rod to push this ball all the way to the end. I need to hear 3 clicks. That gives the highest velocity actually with 3 clicks. And all we care about for the timing, I'm going to reset the photogate. It goes to 0. So all we care about right now is what's the time it takes for the ball to go through these photogates. I already got the distance. So let me draw the first shot. So I'm going to pull on it. So it is 0.0187. So we are going to do another shot. Actually, we'll do 3 altogether, and we'll take the average of these 3 numbers. I don't expect these numbers to be that different. I'm going to reset the time and fire it one more time. And as you can see, it's very close. It's 0.0188. And I will do one more shot. And again, the number should be very close. I push it to the third. And I fire it. And 0.0188, that's the number we got again. So now I'm going to go back to the board and calculate the velocity for this part of the experiment. All right, so in this section, we're going to calculate the velocity of the ball as you fire it from the cannon. We have seen it, that how the photogate actually work. So here are the 3 numbers that we got from the photogate. And as you can see, the timing is really, really small, right? So it is really 100th of a second will be 0.01. So it's a little bit higher than 100th of a second. So we got these 3 numbers. They're very close. So when you add them up and divide by 3, the average number you get is 0.011876. You don't need that much of a precision, but we have those numbers. Let's use them. I have also measured the distance between the photogates, which turns out to be 10 centimeter. Convert that into meter. So you get 0.1 meter. I take that 0.1 meter, that's my D, and my T is over here. I plug that in here. So that divided by that gives me 5.33 meter per second. 5.33 meter per second is a reasonable number. If you think, I always think of it this way, that about 30 meter per second, actually it's 27 point something, or 28 meter per second is 60 miles per hour. So you divide that by about 6, okay? So it will be about 10 miles per hour. That's how the velocity of that ball as it exiting the cannon. So now that we got the initial velocity, this is my initial velocity VI. What I'm going to do is that I'm going to calculate the x and y component of the velocity, and I'll get a pen up from here. But I will let you calculate that. Remember that the theta angle is 30 degrees. So my Vx would be Vi cosine theta, remember theta is 30 degree, plug that in there. Your VI is this, plug that in there. So it will be 5.33 cosine of 30, whatever it is. I will let you calculate that. And Vy initial will be Vi sine theta, and it will be 5.33 sine of 30. Now remember that this guy will be changing throughout the course of the flight, but this guy will be constant. So what I want you to do is, in your write-up, you have some space to calculate the range given these numbers, given your initial velocities. Can you calculate how far the ball will go? Where will it land? So what we're interested in is to find out this distance. So this is my xi, that's my xf, and we're interested in finding xf minus xi. So you have to use the second kinematic equation, which is yf minus yi vyit minus half gt square. I'm writing it down again. And all you do is to plug in these numbers here. One thing I will give you, I have actually measured it beforehand, is what is this yi distance, initial height of the ball. And it turns out to be 1 meter. So when you plug this in here, your final height is 0 meter, -1, and then your vyt would be this guy right here. Let me just plug this number in here for you. Sine 30 degree t, and t is your unknown, that's your variable, minus half. Now use 9.8 in this case, and t squared. So then you take everything on the right-hand side to the left-hand side, and you get a quadratic equation, right? So, and what I'm going to do is I'm not going to solve it for you, and this is the part you have to do at home. But you know that in this case, you can think of this quadratic equation as the solution would be using this formula, right? So use that. What I can tell you is that when you solve it for t, your t would be something in between 0.5 and 1 second, okay? That's what you'll get. Get that number, and then what I want you to do is, you have already calculated this, and your range would be now xf minus xi, which is vx times t. Your x velocity doesn't change. So take everything from here, 5.33 cosine 30, and you multiply that with that t value that you get. So as I said that I expect this to be in between 0.5 and 1 second. When you multiply that with 5.33, I expect something, the range to be between 3 and 4 meters. So we will do an experiment and we'll get that number. What you have to do is that once you finish your calculation at home, I'm going to give you the final number and see how close you came to the prediction, okay? All right, now we are going to actually shoot the cannonball and look where it lands. And we have a carbon paper on the floor, and the carbon paper is right on top of a regular paper, so that when the ball lands on the carbon paper, it makes an imprint. And we can measure the distance from here to where that imprint is, right? So we're going to do it 3 times. We're going to fire the cannon 3 times, and we'll take the average of those 3 distances. And you're going to do that at home. We're going to give you those numbers, okay? For the timing, we don't care about the photo gate anymore because we have already done the velocity part. So all we care about right now, where the ball is going to land. So I have my ball over here. I'm going to push it down to 3. Make sure that I have my angle correct, because remember that it's at it should be at exactly at 30 degrees, because that's what my calculation is for. So I'm going to pull the cord on the count of 3. So I have 1, 2, 3. Okay, one more time. Put the ball in. 1, 2, 3. Okay, let's do one more. One, two, three. All right. So now that I have my three firings, and you know what? Let me do one more firing just so that I don't know whether my second ball actually went in the proper direction. I mean, to the proper distance. So let me actually put in one more shot here. I think I didn't push it all the way down. So let me do this. All right. So you got my three firings. And then what I want to do is that I want to now measure the distance over here. So what we're going to do is that we're going to get a tape measure. And then we're going to go from here to all the way to the end. And Hawaida is going to help us with that. So remember, in your calculation, we said that it should be in between 3 and 4. 300. Do we have the tape measure? Oh, I need that.
It's right there.
Oh, sorry. Right. Between 3 and 4. So here, Hawaida has one end, and I have the other end. And she is going to give me those measurements. And we have the measurements. Our first measurement would be, it's 3.69, and the 3.71, and the other one is 3.68 meters. Okay, thank you. So that ends this part of the lab, and what I'm going to do is that, let me just give you these three numbers over here. We have written them down here, 3.68, 3.69, and 3.71 meters. You take the average of these three numbers, and you're going to use it against the prediction that you got, and just find the fractional error between what you expected and what my results are over here. Okay, so my next part would be, we're going to fire the cannonball at 10 different angles, and you have to go make a graph out of that. All right, we are at the last part of our experiment. This is experiment number 2. All we're going to do is fire this cannonball at different angles. And for every angle, we're going to get a distance. And what you have to do is you have to draw a graph, which will have on your x-axis, it will be the degrees, basically, where you, the 10, 20, 30, 40 degrees up to 80 degrees. And on the y-axis, it will be distance. Basically, you have to figure out from your curve what is the maximum range, at what angle we get the maximum range. Okay, so right now I am set up at 10 degrees. All we're going to do is fire it at 10 degrees and show where the ball lands and how we measure the distance. Then for the next few parts, we are going to skip it. We have done this experiment already for you. And I will go to the board and give you those numbers all the way to 80 degrees. This is just to show how the experiment should have worked if you were here and doing it by your hands. So I put the cannonball all the way in here. I'd have 3 clicks. I think I have 3 clicks. If not, let me just check that. There are 2 of them. That's why. So let me put it back. 3 clicks. It's at 10 degrees. So I'm going to fire it on 3. 1, 2, 3. So it dropped over where the paper is, And we have already done the measurement for you. So this is just to show how things work. So what happens is the next time I just increase it by 10 degrees and I fire it again. And I do this more or less 8 times. And we get these numbers. So what you have to do is you have to get a graph paper and write these numbers down. So I'll go over to the board and show you these numbers. I have the angle on the left column and the distance on the right column. You get 2.77, 3.37, 3.70, 3.72 for 10 to 40 degrees. And then I have 50, 60, 70, 80, 3.42, 3.03, 1.9, 0.8. You can see that it's somewhere here, it's starting to peak. If it was absolutely flat ground and the firing was symmetric, that means that your y coordinates are the same at the start and at the end, then we expect this to actually peak at 45 degrees. So, but that's not the case here because we are at a higher ground, so there is a little bit of asymmetry, but you can still see that it's somewhere in between 40 and 50, you'll get the largest range. One thing about this lab is that we didn't take into account the air friction, and it didn't bother us that much actually, I can tell you that. But if you are thinking of like military, army firing, artilleries and things like that, or you're in a football match, you're throwing that football, so the air friction is a big deal in that case. You cannot really simplify this with our quadratic equation that we use today. You have to do an integration to get the right answer. But those are done by computers and things like that. And when you throw a ball, whatever, it doesn't matter what game you're playing, baseball, football, soccer, because as the ball turns, there is wind, and the wind and the ball itself will have interactions between them, Bernoulli principle, all kinds of things. So, but for this experiment, we can safely ignore the air friction as far as we're concerned, actually, to get to the point. Okay? So the last section of this lab will be, I'll show you the write-up and exactly where you have to put your numbers in. Okay? Okay, so we're at the very end of our projectile lab, and this is your write-up, and you have to basically write down your results here and do all your calculations and submit this write-up. So our name of the lab is Projectile. Here the objective, you have to predict where the ball is going to land and then verify the range. And actually we have done the verification for you, and we have given you the number, but you have to predict using the velocity that we are giving you. Okay, so this is the theory part. We went over that in the class and today also at the very beginning of the lab. And this is the setup. You already saw that in our video earlier. And let me just go down. And this is where you have to write in your, even though we have given you the average number already and the initial speed, but I want you to redo this part here. Remember, d is 10 centimeter, which is 0.1 meter, and you get the initial speed. We actually gave you the initial speed, which was 5.33 meter per second. Then what I want you to do, this is the part you have to do, you show your calculation here, is using that velocity and also the angle. The angle is 30 degrees, remember, angle above or below horizontal, that's just above the table. There is a place where you can put your angle, it's 30 degrees. And then use that to find out your Vx and Vy component and solve that quadratic equation, yf equals yi plus vi initial yt minus half gt squared to get the time. And the time will be, as I said, between 0.5 and 1 second. And then use that time to find the predicted range. It should be also should be between 3 and 4 meters. And here's the calculation. You do the calculation here, write down the predicted range, and then confirming the predicted range. This is the part we already did for you. So it would be 30 degrees again, and calculated time of flight. You write down what you got, and the predicted range what you got. And then these are the distances we gave you. We fired it, and actually we gave you those distances. If you don't remember, go back and look at those numbers one more time, and then get an average and do the fractional error between your predicted number that you got and the measurement number that we gave you, and get the fractional error between those two. So I hope you got this part correctly and your fractional error is not too high. I cannot really say what kind of fractional error we're expecting. It shouldn't be not more than 10 or 15%. Then let's go over to the second part of the experiment. So this part we already gave you some numbers on the board, so you can just copy it back. Notice that our tables are slightly different, because if you are in the class, then you could have actually done this, taken time and do this. In this case, all we have done, we have given you in 10-degree intervals. So what we had here is a 10-degree, then instead of 30, we have 20. So you have 10, 20, 30, 40, 50, 60, 70, 80. So don't worry about what the numbers are written here. You can just plug in your angles over here and write down the distances that we gave you. And then what I want you to do is your angle will be x-axis, your distance will be y-axis, and see if the curve looks like a parabola or not, and for which angle you have the maximum range. That actually concludes the lab by itself. There are a few things I want you to do at home, and I want you to review this concept. For example, why is this curve is a parabola? So go through this and see how I actually substituted the time in our y equation, kinematic equation, and got an expression that looks like a parabola. See that x squared? So y equals x squared. This is the equation for a parabola. So review that. And then I said draw the above curve in wolframalpha.com. You don't need to do it for the time being. We are going to go through Wolfram Alpha on a separate video in the class. So I will come back to it. Right now, you can just draw that in a graph paper. Sorry, I beg your pardon. I meant draw this curve on the Wolfram Alpha, not the previous experimental one. This curve you have to draw on Wolfram Alpha, but I will show that in the class how to work with Wolfram Alpha. And then answer the following questions. What is the maximum height of the ball in experiment 1? Just use your kinematic equation to find, because I have given you the velocity and the angle. From that, actually, you can calculate the maximum height very easily. Do that and find the time it takes to get to the maximum height. Also use kinematic equation to do that. And then this is also in the textbook. It is just a theoretical part. If you launch the ball from the ground and receive it at the ground, then show that you can express the range as simply with this analytical expression. You don't have to do any, as long as you know the initial velocity, you would know exactly where the ball lands, except for the fact that you have to ignore the air friction. If you include air friction, this becomes too complicated. So that ends the Projectile Lab. I hope all of you enjoyed it. Rest of it we can discuss in the class or during the office hours. Thank you.